So let's come back to this question now. Okay. So what is happening here is that there is.
So just a minute. So just a minute.
Okay, so let's understand this question in detail now. So this metallic rod or cylinder is in steady
Sir, 1
state.
minute.
It's okay, you can continue solving it if you have got the idea what to do. So what is happening is this end of the cylinder is inside the heat furnace. So it is being maintained at a constant temperature of, how much is it? 227. So that's 500 Kelvin. Whereas this end, its steady state temperature is 127 degrees C or 400 Kelvin. And the surrounding temperature is 300 Kelvin. whereas this part is all insulated. So because there is insulation here, so the heat transfer is happening only via conduction inside. And via radiation here. So the rate of heat transfer by conduction, so this point is A, from A to B, must be equal to net rate of heat loss by radiation at surface.
सर एक सेकंड क्वेश्चन दिखाओगे?
Sorry, what?
एक सेकंड क्वेश्चन दिखाओगे सर?
Question?
हाँ सर.
Okay.
Done sir, thank you.
Okay, so the rate of conduction, as you know, is this quantity. And the net rate of heat loss will become E sigma into the same surface area as the cross-sectional area here, into T2 to the power 4 minus T0 to the power 4. So in this equation, you will see ultimately L is the only unknown. So substitute all the values. K is given to us as 200. Area will anyway cancel out. Emissivity was 0.4. Sigma we are taking as 6 into 10 raised by minus 8. A I have cancelled out. And this is 400 to the power 4 minus 300 to the power 4. So this equation will give us the length. So this is giving us a length of close to 48 meters.
Suggestion.
So that is the first part, to find the length of the rod. The second part, we have to find the rate of heat generation by the heat source inside the chamber, inside the thermal chamber, which is maintaining this end at a constant temperature of T1. So in that, of course, you have to assume that the walls of the thermal chamber are perfectly insulated. So all the heat generated by the heat source is just getting lost by conduction. So the rate of heat generation is nothing but the actual rate of heat conduction in joules per second or watts.
Done.
Yeah, now work out the second part, the rate of heat generated. So this rate, which is the rate of conduction, which is ultimately the rate at which the heat is getting dissipated by radiation, this only is the rate of heat generation inside the thermal chamber. So we can calculate it either by calculating the right hand side or the left hand side's value of the above equation. Now, since we've already calculated the value of this length, we can just go with this. Now we'll need to plug in the value of the area of cross section, 5 centimeters square. Into this temperature difference. So this will become our rate of heat generation in joules per second or watts. So it will be nearly 20, slightly greater than 20. Actually closer to like 21. Okay, so hope this question is clear.
Just 1 minute. Excuse me, sir.
So understood this concept now, why this rate of generation, heat generation, it's exactly equal to this rate of conduction, which is exactly equal to the net rate of heat loss due to radiation at the other end. That's how the metallic cylinder is maintained at steady state, because the rate at which it's drawing heat from the heat source at the left end is exactly balanced by the rate at which it's losing heat because of radiation at the right end. And the transfer from left to right is happening by conduction through the rod.
Done. 1 minute.
Okay, now next thing we'll go back to the fundamentals of Newton's law of cooling, and we'll see how to solve for temperature as a function of time. But before that, we'll also see the connection of Newton's laws of cooling with Stephen's law of radiation. So let's examine the individual statements of each of these. So what Newton's law of cooling says that if the surface temperature is equal to the surrounding temperature plus a certain amount such that delta T is small compared to T naught, okay, where T is surface temperature of a body in kelvins and T naught is the surrounding temperature or the atmospheric temperature around, again expressed in Kelvin. Then the rate of cooling is directly proportional to the temperature difference. This is the statement of Newton's law of cooling. So mathematically, this works down to this rate of cooling is directly proportional to the temperature difference. Or in other words, we can say that the instantaneous rate of cooling must be equal to some constant into delta T, whereas K is some physical constant. Okay. Now let's see how this compares with what Stephen's law of radiation says. So what Stephen's law of radiation says is that if some surface is at temperature T and surrounding is at a temperature T naught, where T is equal to T naught plus delta T, then the net rate of heat loss, we just saw, minus dq by dt should be equal to E into sigma into surface area into temperature of the body to the power 4 minus temperature of the surrounding to the power 4. This is the statement from Stephen's law. So what's the connection between these two? Let's understand that. So now if we apply this condition over here, that delta T is small compared to T naught. So T is equal to T naught plus delta T, where delta T is small compared to T naught. Then this term that we have inside the bracket here, T to the power 4 minus T naught to the power 4, can be expressed in a slightly different way using a binomial approximation. So here if we take T naught to the power 4 common, we have 1 plus delta T by T naught to the power 4 minus 1. Now because of this condition that we are taking delta T small compared to T naught, so we can take this power inside. We can use the binomial approximation. So as delta T by T naught is small compared to 1, because we are assuming that delta T is small compared to T naught. So we can approximate this term this can be approximated as T naught to the power 4, 1 plus 4 times delta T by T naught. Instead of 1 plus delta T by T to the power 4, it becomes like this, minus 1. So this is the binomial approximation step. Basically, is this theorem that 1 plus x to the power n can be approximated as 1 plus nx if x is small compared to 1. So here n can be any real number, okay, including a negative value, fractional value, whatever. Here it is 4. Okay. And x should just have a magnitude which is very small compared to 1. So here x is delta T by T naught, which is obviously small compared to 1. So then this term gets further approximated as, so 1 and 1 will cancel. So 4 times T naught cube delta T. So now you can see that our net rate of heat loss is going to become proportional to delta T, provided of course this condition is satisfied. The delta T is small compared to T naught. So then you will see that our Stephen's law of radiation will be in agreement with the experimental law, which is Newton's law of cooling. that the rate of cooling is proportional to delta T. Because otherwise what Stephen's law says that it's not proportional, it's proportional to T to the power 4 minus T naught to the power 4. Whereas this one says it's proportional to T minus T naught. So what is the connection between the two? This is a conditional statement. Okay, this statement is only true for delta T being very small compared to the surrounding temperature. So when I apply that condition to Stephen's law of radiation, then the binomial approximation shows me why this condition comes true. So we'll just solve this a little further. First note down up to this point. So through this, we'll be able to explore the relationship between Newton's law of cooling and Stephen's law of radiation. So of course, Newton's law of cooling was established long before Stephen's law of radiation was, because it was based on experimental analysis of bodies just naturally cooling in an atmospheric environment. Whereas Stephen's law of radiation was established on the basis of much more advanced, experimental work in radiation. So it came quite a bit later in history compared to Newton's law of cooling. So if you look at the individual statements, it seems that they are contradicting each other. But if you apply the condition that delta T is very small compared to T naught, then you will see that ultimately Stephen's law of radiation also agrees with the observation from Newton's law of cooling. Okay, so now if we substitute
One minute,
this,
1 minute.
so still writing, okay. Okay, so have you tried the substitution yourself now? So you can see that the net rate of heat loss will become E sigma into S into 4 T naught cube delta T. Okay. Now further, if the particular body we are talking about has a heat capacity equals to C, okay, so then dq is heat capacity into change in temperature, so minus dq by dt net can be written as minus C into rate of cooling, so that is becoming E sigma S into 4 T naught cube delta T. So you can see that you get this, that the rate of cooling is proportional to delta T, and the constant of proportionality is equal to, it depends on all these things: surface area, surrounding temperature, and the heat capacity. It depends on all these things. Okay. So in case the body is an isotropic solid, then the heat capacity can be written as mass into specific heat capacity. So don't confuse the small s with the capital S in the numerator. Capital S in the numerator is the surface area, whereas this is small s, which is the specific heat capacity. Okay. So you can see how this is in agreement with Newton's law of cooling. So Stephen's law of radiation reduces to Newton's law of cooling, provided, of course, we have that condition that delta T is very small compared to T naught.
Sir, can you scroll up once? Yeah, sir, you can scroll down.
Okay. Okay, so let's look at an example based on this
Sir,
kind
one
of
second.
concept.
Sir, just a minute.
This
Sir,
kind of
1 second.
concept. Okay, done.
Yes.
So 1 minute. So just a minute. Just a minute. Done, sir.
So let's see a typical kind of example where this kind of concept comes into question. So we are comparing two objects, two metallic spheres, let's say. They are having different size as well as they are made of different materials. So this is a solid metallic sphere A. Now this particular sphere has a radius of, let's say, 9 centimeters. It's made of metal which has emissivity equal to 0.6, okay, density equal to 8 gram per cc, and surface temperature is maintained at 30 degrees. So the metal of sphere A has these particular properties. Now this second one, this is also a solid metal sphere, okay, but it's a different metal compared to the first one. So its radius is different, of course, because you can see the size is different, but also the emissivity of this particular metal is 0.5 and its density is equal to, say, 9 gram per cc. Yeah, and one more thing that had to be given, I forgot, is the specific heat capacity. So the specific heat capacity of this metal, let us say, is 0.2 calories per gram degree C. And the specific heat capacity of this metal is 0.25 calories per gram degrees. Now this one's surface temperature is also maintained at the same value. Oh, sorry. Yeah, let's take same value. So this is also maintained at 30 degrees C, and the surrounding temperature is 27 degrees. Okay. So if the rate of cooling for the sphere A at the given instant when its surface temperature is 30 degrees C is, let us say, 25, or rather 2.5 into 10 raised by minus 3 Kelvin per second, then find the rate of cooling for B when temperature of its surface is 30 degrees C, or when temperature of its surface is 28 degrees. Okay, so in fact, let's do this question this way, that the radius is actually unknown, but only the ratio of the radius is known. So if this radius is some r, this radius is 2/3 of r. Rest of the details are known. So you'll see that basically you have to apply Newton's law of cooling here, because when you convert the temperatures to Kelvin, you will see that the surface temperature of A and B, the difference with respect to the atmospheric temperature is very small compared to the atmospheric temperature. Okay. But remember, to gauge that condition that delta T is very small compared to T naught or not, you have to apply, you have to take the temperature in Kelvin. You should not take the temperature in degrees C. So once you see that condition is satisfied, that delta T is very small compared to T naught, you know that Newton's law of cooling is applicable. But when you compare the two spheres for Newton's law of cooling, you have to understand how to develop the constant of proportionality. So that is where the comparison with Stephen's law of radiation that we just saw, okay, where the constant of proportionality depends on all those things, the heat capacity, the surface area, okay, the emissivity, all these things. Okay, so let's understand this. So first, let's understand the constant of proportionality for a spherical body. Then we can come down to comparing the two. So if this spherical body is at temperature T, surrounding is at temperature T naught, such that delta T, which is T minus T naught, is small compared to T naught. Okay, then this is equal to E sigma into 4 pi r square into T to the power 4 minus T naught to the power 4, which will then approximate as E sigma into 4 T naught cube into T minus T naught. Okay, so this is the approximation step. This whole term will get approximated as this term by binomial approximation. Meanwhile, on the left hand side, this, if it has mass m, specific heat capacity s, radius r, then heat capacity is m into s. So that is density into 4 by 3 pi r cube into s. Okay. So this minus dq by dt, which is minus of heat capacity into dt by dt, this will become minus of density into 4 by 3 pi r cube into specific heat capacity. That should be equal to E sigma into 4 pi r square is T minus T. So this will give us an idea of the proportionality. So the rate of cooling this will be, you will see 4 pi r square will cancel off on both sides. So we have 4 E sigma into T naught cube, okay, divided by density into R into S into a 3 also going on top. So this kind of term into T minus T naught. So you can see that the constant of proportionality for Newton's law of cooling being applied is basically this term. So we will use this relation for individually A and B, but we'll understand that K is a term like this. It is directly proportional to emissivity. Sigma is of course a universal constant. T naught is also same for both of them in the same environment, but it's also inversely proportional to density into radius into specific heat capacity. So this is what we'll need to check. Okay. So now just apply this concept to the data given for the two spheres and you should be able to answer the question. Okay, so let's compare the two quantities here. So you can see that if you talk about the rate of cooling for sphere A with respect to the rate of cooling for sphere B, this is going to be the ratio of the emissivities into inverse of the ratio of the densities into inverse of the ratio of the radii into inverse of ratio of specific heat capacities into, in general, it will be like this also. But for the first part, obviously, both the temperatures are the same. So even this will be the same. So you can just use this relationship. So you can see that the ratios of emissivities is 6/5. Okay. Densities is 8/9. So let's just pick up all this data. Now for the first part, you're taking the temperature of B also as 303 Kelvin. So this ratio will be 1:1. So from this, you can find out the rate of cooling for B. So you just have to inverse all this. So be this much in kelvins per second. And for the second part, when the temperature of B becomes 28 degrees C or 301 Kelvin, okay, the rate will just become, so the temperature difference has changed from 3 Kelvin to 1 Kelvin. So this rate will become 1/3 of the rate that you calculated above for the temperature being 30 degrees C. So whatever rate you get over here, you just substitute that value here and you will get the rate when the temperature is 28 degrees C. So it's quite easy really. So, but this thing is important that Newton's law of cooling doesn't really give any information about the constant of proportionality in its original statement. But when you apply the additional knowledge that you know from Stephen's law of radiation, then you understand what that constant of proportionality exactly is and how it depends on all these factors.
So can you explain that second part again?
Second part में देखो क्या हो रहा है ना, B का surface temperature it has reduced at some stage from 30 degrees C to 28 degrees C ना.
Yes.
So what has happened to its rate of cooling? Now rate of cooling is directly proportional to temperature difference with the surrounding.
Yes, sir.
So now your surrounding atmospheric temperature is not going to change. Now it's going to remain 300 Kelvin. Whereas the surface temperature has changed from 303 Kelvin to 301. So temperature difference कितने से change हो गया? 1/3 हो गया.
Okay, sir. Got it.
Earlier it was 3 kelvins, now it is 1 Kelvin. So the temperature difference delta T has become 1/3 of what it was. So the rate will also become 1/3. All other parameters are same, na?
Okay, sir.
Okay, so this is another type of question, especially for JEE Advanced, which relates to Newton's law of cooling, but you have to apply your knowledge of Stephen's law of radiation also. Okay. So it's not really a direct question, the type you expect in JEE Mains.
So 1 minute, sir.
Yeah. Okay.
Done, sir.
Okay, done now. Okay, now
Sir, just a
one
second.
more. Yeah. Sorry.
Sir, just a second, last slide. Done, sir.
Okay. Now moving on to another type of application of Newton's law of cooling. When we want to find the temperature as a function of time using the rate of cooling. Okay, so temperature as a function of time for a situation where again the surface temperature is equal to T naught plus delta T such that delta T is small compared to T naught. So by Newton's law of cooling, you have that the rate of cooling is some constant into this temperature difference. So now suppose I have a situation that at T equal to 0, the value of the surface temperature is some initial temperature. And let's do this with an example. So for example, this initial temperature might be 305 Kelvin. The surface temperature is, let's say, 300 Kelvin. Okay. Now we want to find that at a general time T, okay, what is the temperature? Okay. And also given to us additionally that at T equal to 0, the rate of cooling this was equal to, let us say, 0.5 Kelvin per minute. So generally cooling takes place very slowly like this. Okay, so especially if it's a body of large surface area and all that. Okay, so if the rate of cooling initially at T equal to 0 is equal to 0.5 Kelvin per minute, then how we'll find the temperature as a function of time. Okay. So what happens is that this is basically what we call a differential equation. It's an equation between that relates this rate versus the temperature. So now to get temperature as a function of time, we need to integrate the differential equation. So this above equation needs to be integrated. So let's understand it in principle first, then we'll put the values. So this is equal to this constant into T minus T naught. And keep in mind that even the surrounding temperatures are constant. So not N naught. T naught is also not changing with time. This is also constant. And of course, K is a constant. Okay. So if we rearrange this equation, we can see that we get this. We put each variable on each side. So temperature is on the left hand side and time is on the right hand side. So we can see that during a small time dt, the change in temperature capital DT is this much. So over a long period of time, what about the change? We can get that by integrating this. So now when we integrate this left hand side, correspondingly we'll integrate the right hand side and we'll put the limits that at T equal to 0, the temperature was how much? Whatever this initial value was. Let's say that is Ti, and at T equal to T, the temperature is some value which we want to calculate. So this is just like you have seen application of integration in kinematics earlier, okay, or in other parts of mechanics also. So that kind of thing. So a rate of change is known. So from that rate of change, how do we know the function itself? By integrating it. So we know rate of change of velocity is acceleration. So then by integrating that rate, we get the velocity. So like that, if we know rate of cooling, then by integrating that relation, we can find the temperature itself as a function of time. So next, let's see this integration. Okay. So we will use this integration that we know integration of 1 by x is ln x. Okay. So integration of 1 upon a linear function where a and b are constants is like this. Okay. So that is like that over here. So this will become minus sign is separate. Okay. ln of t minus t naught. On this we have to put the limits t equal to initial value to some value t which we want to find out. On the other side it is just k into t because k is a constant, integrated from t equal to 0 to t equal to t. So next step we can Just take the minus sign on that side and we can write this as ln t minus t naught upper limit minus ln t initial minus t naught lower limit is equal to, I've taken the minus sign on that side, so it's minus kt. Then I'll use the property of log that ln a minus b is, that is ln a minus ln b is ln a by ln b. It becomes this. And then we can take exponential, because we are finding out temperature as a function of time. So we will get this kind of value. Temperature at any instant will be this kind of a function. It will be an exponential function which is decaying with respect to time, because it is e raised power minus t kind of graph. Okay. Now let's also simultaneously understand this with the example. So how would we execute this numerically for this given example? So if we had this data, okay. So from this data, what we can see here is T initial is 305 Kelvin. Now also we can see that initially the rate of cooling at T equal to 0, that would be equal to K into initial temperature minus T naught, and that is given to us as 0.5 Kelvin per minute. So this is indirectly giving us the value of K. So K into 5 Kelvin is 0.5 Kelvin per minute. So the value of K over here, now let's not confuse Kelvin and small k. So this constant of proportionality is 0.1 minute inverse. So I have this data and I have these two values. So now I can substitute that here and I can find out that the temperature at any time t is T naught, which is 300 Kelvin, plus the initial temperature minus T naught, which is 5 Kelvin, into e raised power minus 0.1 T, where because that 0.1 is in minute inverse, so T should be substituted in minutes, and the temperature we'll be getting will be in Kelvin. So this is how the temperature is varying with time. When we use this in this particular numerical example, this is how we will be able to calculate temperature as a function of time. Okay, so this is the process. Okay. Just start with Newton's law of cooling, which is expressed as a differential equation, and integrate that relation to find temperature as a function of time. So that integration step is done over here.
So please scroll down a little.
Sorry, beta, come again.
Can you please scroll down a bit?
Yeah. So this is the final value. Okay.
Done, sir.
Okay. So one final thing about this. Now, when we visualize this as a graph, how the temperature is changing with respect to time. So you can see from this that, or from this that at T equal to 0, the value of the temperature will be equal to T naught or 300 Kelvin. Because this factor e raised power 0 will become 1. So sorry, it will be T initial, not T naught. It will be equal to T initial, which is equal to 305. Because e raised power 0 will be 1. Like that. So this factor will be 1. So 300 plus 5 or T naught plus Ti minus T. Okay. Whereas as T tends to infinity, what will happen? E raised power minus infinity will tend to 0. So this whole factor tends to 0, or here this factor tends to 0. So the temperature tends to become equal to the surrounding temperature. So that is why it's called an exponential decay. The temperature is decaying with time, very slowly but exponentially, in such a way that this is how the temperatures behave. It's not decaying to 0, but it's going to decay to the surrounding temperatures value, which is T naught. Let's say this is the value of the surrounding temperature. So with time, the temperature will gradually decay. Like this. So this also shows you that the rate of cooling is decreasing as the temperature is decreasing, because the slope of this graph is decreasing. So this one's slope only, no? The slope is the rate of cooling. So you can see that the rate of cooling is decreasing as the temperature is decreasing, because the graph is, it has that kind of concavity that its slope is decreasing with time. Okay, so this is the final analysis of Newton's law of cooling. Okay. Yes, last lecture's notes I have not sent, is it? Yes. Okay, I'll send them. Yeah, next lecture we should be able to begin fluid mechanics, but I will keep some time for doubts of heat transfer also. So next week definitely we'll start fluid mechanics. Okay.
Sir,
You've covered
also
all
the
the types of
DPT,
questions. Yeah, sorry.
DPT doubts of heat and thermo.
Of which one?
Heat and thermo DPT.
Heat and thermo doubts. Acha, DPT. Okay. DPT you still have doubts. Okay.
Sir,
DPT, I'm not having any.
I had one doubt. Question that answer is wrong. that you have to change it in highest temperature. There were Fahrenheit, Kelvins, and degree Celsius. So 13 degree minus 13 degree Fahrenheit is 25 degrees Celsius.
Okay, just send it to me on WhatsApp. Now I'll take a look at the question and confirm for you. Okay. So next time I'll keep some time for doubts. I have a meeting today right now, so I have to like quickly wind up. Otherwise, I would
Okay,
have
sir.
some time now also. Okay. So next week, one of the lectures will keep time for doubts of heat and thermo, whatever is pending. Okay.
Okay, sir.
Including DPT and everything. So
Okay,
that's
sir.
it for today. People, wish you all the best.
Bye, sir.
Bye, sir. Thank you, sir.
Hi, sir.
Sir,
Bye, sir. Thank
Yeah.
you, sir.
Yeah.
sir, there has not been any mentorship lecture in this month in Yellow House.
You can contact this person, Mr. Rahul Singh. You can talk to him once about scheduling, right?
Okay, sir. Thank you.
Okay, I'll put in the word that there's been.
Okay, sir. Bye, sir. Thank you.
Okay.